This problem we're asked to do an energy balance on heat exchanger. We're given the feed, which is superheated steam, and we tell how much energy is removed from that steam to heat some reactor feed. We want to know what's the outlet temperature of the steam, what phase is it in, and then what's the enthalpy. So first thing we want to do is draw a diagram so we can input the information we already know about the system. So here we're showing the mass flow rate in, m dot. That's a constant, so the same mass is leaving. We don't know the outlet temperature, and the heat removed is negative. That's, I'm taking as my system the steam, so I'm removing 450 kilojoules per second, which corresponds to 450 kilowatts. So what I want to do is an energy balance. It's a steady state system, and so the energy balance is going to be steady state. We have energy flowing into the system, an inlet stream, same mass flow rate out, enthalpy is going to be different, and then we have a rate of heat removal. Of course, in general we would have work, but there's no work in this system. The first thing we're going to do is look up the inlet enthalpy using steam tables. So 200 degrees C, 10 bar, and go to superheated steam tables. And we know it's superheated, one, because this pressure is less than saturation pressure, and because a problem statement points it out. And so the enthalpy I can just read directly. The enthalpy coming in, 28 kilojoules per kilogram. I can solve this equation for the enthalpy out. So let me first rearrange the equation, the energy balance. So I rearrange the energy balance by taking these two terms the other side of the equation. And then I substitute in the values for Q dot and M dot. And so H out is just Hn minus 225. Hn, something we just looked up in the steam tables, 28. That's kilojoules per kilogram minus the 225 kilojoules per kilogram. And so the enthalpy out, in order to determine the temperature, we go back to the steam tables. And what we notice is that if we look at enthalpy at 10 bar for saturated vapor, the enthalpy 2,777 kilojoules per kilogram, which means since we have a value less than that, but we're at 10 bar, we must be in the two-phase region. And so that means we're at saturation conditions. We can calculate the quality because the enthalpy is a mixture of so much vapor, so saturated vapor, and so X is the fraction of vapor, 1 minus X the fraction that's liquid. Enthalpy liquid saturation conditions. We know the total enthalpy, that's 2603 kilojoules per kilogram. So I'm going to write down the values from the steam tables for saturated liquid, saturated vapor at 10 bar. So we can solve for X, the quality, and X is 0.91. So that means we know the temperature leaving. It's one of the things we wanted to determine. And that's the saturation temperature at 10 bar, 179.9, which significant figure is 180. We now know the quality, so it's wet steam that's leaving. And its enthalpy, 2603 kilojoules per kilogram. That's the information we're asked to determine.